Last time, on the tutorial. It's WebGL. It's creating a shader program.
It's not just a vertex shader, it's a fragment shader.
Listen to me, Mahoney. This thing's imported a texture coordinate buffer, and soon it's about to import a geometry buffer. If you can't get the job done, I'll find somebody who can. You can't fire me if I quit.
Do you see it? It's imported an image, and it's displaying it too.
And what the hell are we gonna do now?
And now, the continuation.
Hello, my name is Bertie and welcome back to the tutorial. This is part of a series where we're using WebGL and JavaScript to write a 2D game engine in the hopes of teaching you a little bit of the basics about a game engine and a little bit about OpenGL at the same time. So last time we left off, we were working on this here. This is where we stopped. We had two sprites displaying on screen, admittedly upside down. So today I'm going to hopefully walk you through the steps of getting these sprites animated and moving. This is one I did earlier. You can see this one sprite's walking across the screen and both of them are animating. That's where we hope to get to today. They're also facing the right way up and, you know, they're displayed using the available screen space and everything else. So I suppose let's just get cracking. Before we get started, I want to make a quick trigger warning. Today we're going to be working with Matrices, which is some... well, I was going to say high-level maths concepts, but it depends on your definition of high-level, I suppose. But they're probably something a lot of people who don't have experience with writing engines before may not have come across, and it'll require some explanations. So what is a matrix? So I got myself a very advanced paint program here to illustrate the point. So a matrix is just, it's an array or a square or grid, whatever you want to call, of numbers. So this is, we'll call this matrix A. So a matrix, like I say, just a grid of numbers. So we have 0, this is going across the top row, 0 or 1, 0, 0, and then in the next row you have 0, 1, 0, 0, okay, and then we have 0, exciting I know, 0, 1, okay. So yeah, a grid of numbers. So we have three we have three rows and we have three columns. Now, not all matrices are going to be, you know, 3 by 3. This happens to be a 3 by 3 matrix, which is going to be useful to us. But a matrix can be any shape. You know, it can be anything from 2 by 3 to, I don't know, I've never seen one, to n by m. So they can be of arbitrary size, but today we're going to be working with 3 by 3 matrices. And so, like, what are they? They're just they're a convenient way of packing up numbers, and they have their own algebraic rules that I'll explain as we go along. But they're incredibly convenient ways of packing in what we're going to call transformations. So if we have a 2D shape on screen, we can use a matrix to manipulate that in a very convenient and pleasant way. A great tool to illustrate what a matrix can do is this website here. It's called ncase.me matrix, and here we have some 2D points. These are just vectors or points or whatever you want to call them in 2D space. So you can see here they all have different values forming this M, which is represented here by this X and Y. And then here's this 3 by 3 matrix I was talking about. And so it's got some values, like it's got the same values I set up. So it's got 1, 0, 0, 0, 1, 0, 0, 0, 1. And this is a special value. This is the identity element. And if you don't know what an identity element is, it's an identity element is the value in which an operator will return the same result. Now what that means is the identity element of addition will be 0 because any number plus 0 is still any number. 5 plus 0 is 5. In multiplication, the identity element is 1. So any number times 1 is still any number. 10 times 1 is 10, 12 times 1 is 12, so on. So that's what an identity element is. And then an identity element in a matrix multiplication is this here. A sort of diagonal of 1s is how I think about it. There's like a 1 at the start and there's 1 in the middle and there's 1 in the end here. And if you take any value of x and y, here we have -1, -1. If we multiply it by that identity matrix, we get -1 and -1 at the end. We get the same result. So when you multiply this matrix by this vector, we get the same result back out again. But whenever we start changing the values of this matrix, now whenever I was trying to learn this, I didn't have a tool like this and was incredibly unintuitive, but I think you should have a play around with this tool, because what it really shows, if I start changing these values, so if I change this 1 and start increasing it, we see that the scale along the x-axis starts increasing. So if I put in 2 here, we can see now it's double the width that it was. And again, if I put a 2 here, it's now double the height. And with them together, it's scaled double in both axes. So this new M we've created is twice the size of the original M. So you start getting an idea that why this is sort of useful for 2D programming, because by changing these values, we can very quickly multiply all these points by this matrix and have a consistent result. Now, speaking very broadly here, obviously there's a bit more to this, but yeah, these three diagonal numbers effectively represent scalars. So you saw the M changing size as I changed these values. These 2 values on the right column, they're the transition, the offset of the points. So as I increase 1, the entire thing shifts over 1 unit to the right, and then if I increase 1 along this middle row, it moves this M along that axis, the y-axis, and likewise we're going to minus numbers, does the same thing. So if I want to change the position of, like, if you can imagine I want to change the position of a 2D object, I can then change the right column of my matrix as a convenient way of making all those transitions happen evenly. And then these 2 numbers here, which is the middle on the top row and the left in the middle row, sorry, these terms, these sort of, if I change this value, you can see it starts, I don't know what you describe that as, it starts sharing. And with the right application of values, we can create a rotation. So this M is effectively now rotated about, I don't know what that would be, about 35 degrees. And so with the right application of arithmetic, we can now achieve a 45 rotation. Obviously, it would have to be scaled down a little bit as well. So if I scale down about 0.7, we have something that's roughly the same size as what we started, now at a 45 degree angle. Anyway, that gives you an idea of how useful this matrix is. But let's talk about matrix algebra. So we have our matrix here. This is an identity matrix. And we want to multiply this matrix, or our vector, which is, our 2D position, by this matrix. So we define our 2D vector is a column vector, which just means it's vertical. So we give it some values. We give it an x value of 1, y value of 1, and a z value. Now the z value is always going to be 1 because we're not using z values. We've got a 2D point. But for matrix comprehension, we do need something with the same number of rows as our matrix. So we put in this effectively redundant number at the bottom for our z. So it's always going to be 1. Now, you don't really have to worry about this stuff in general. If this is too complicated or a little high level, it's not really important that you understand this, but just more to know that that this is what a matrix does. You can just copy it, download a matrix library, just skip over this step and copy somebody else's code. The point is, I just want you to know this is what's going on under the surface. In 3D programming, if you ever step into that world, you'll be using something called quaternions, which is the same as this 3x3 matrix, except for it's got 4x4, and basically the same thing. We have our 3 rows, and if we go back to this website here, the one I was illustrating with, you can see, yes, this indeed does have the superfluous 1 at the bottom as well, so we can multiply across this bottom row here. And then you can see that, here's the actual algebra here. If I hover my mouse over these different values, you can see what actual comprehension is happening. So it's 0 times y. So we have 0 in this column, or sorry, in this element here, and we multiply it by y. And then these values you can see that these different values and how they correspond. So these free calculations added together gives us our product x for our final vector. And then you can see it's largely the same thing here, except for it's using the second row. And then the same thing here, only it's using the third row. So just to show this in action, I'm going to do this little example for you. I put in some values here, 2, 0, 4, 0, 1, 1, 0, 0, 1. And for our vector, we have an x value of 1, a y value of 0.5, and a z value is always going to be 1. So we start off here with the values 2 times x, which is 1, plus 0 times y, which is 0.5, plus 4 times z, which is 1. Then for the next row, we have 0 times x plus 1 times y plus 1 times z. And for the bottom row, we have 0 times x plus 0 times y plus 1 times z. Okay, and if we do those calculations, 2 times 1 is 2, plus 0 times a half is 0, plus 4 times 1 is 4, then 0 times 1 is 0, plus 1 times 0.5 is 0.5, plus 1 times 1 is 1. Then 0 times 1 is 0, plus 0 times a half is 0, plus 1 times 1 is 1. And then we just do those additions. And so 2 plus 0 plus 4, that is 6. 0 plus a half plus 1 is 1.5, or 1.5. 0 plus 0 plus 1 is 1. And if we go back to our little application that we're using to help us, I've already plugged in those values, and you can see that that is correct. That's the same results that we got. And that's how you multiply a vector with a matrix. Multiplying a matrix with a vector is all well and good, but we're also going to need to know how to multiply one matrix with another matrix. You'll need to do this because you'll set up one matrix transformation for a vector, but then you'll also want to apply a second matrix transformation to the same vector. And to do this, you'll have to multiply the two matrices together before you apply it to the vector. So let's just get started with that. This is another really good website here, and you can see it lets me put in some 3x3 matrices, calculate them and get the results. And you might find this useful too when you go to implement this, to actually test your matrix to make sure you get the right results back. So I'm going to show you here the algebra of multiplying two matrices together. So I have matrix A and matrix B, and we're going to multiply them together into matrix C. So a good way to remember this is if you want to find out a value, say this first value, is to consider its row and column position. So it's on the first row and it's on the first column. So we want to start using the values from the first row of matrix A and the first column of matrix B, and we go through them 1, 2, 3, 1, 2, 3, and we multiply the values of 1 and 1, 2 and 2, and 3 and 3 together. And once we have those, we add the results of those multiplications together that form the final value we get for C. So let's just step through that. So we want to find this value of C here. So what we do is we take value 1 and value 3. So 1.0 times 3.0. And we add that to the next one. So the second one is 0 times the second one here is 0 plus 0 in the third one times 0 in the third one there. So 1 times 3, that's 3. 0 times 0, that's 0. 0 times 0, that's 0. So add them together. 3 plus 0 is 3. So our first value is 3. So what about the one beneath it? So this is on the second row, but it's still in the first column. So we move down to the second row of matrix A, and we get those values. So our first value is 2 times our first value 3 plus our second value, which is 5, times our second value, which is 0, plus our third value, which is 0, and a third value, which is 0. So 2 times 3 is 6, 5 times 0 is 0, 0 times 0 is 0. So 3 times 2 is 6, so 6. This value here is 6. And I think that's going to start making sense to you. So we want to do the middle one. So our middle one is on the second column and the second row. So we use the second column from B and the second row from A. So let's clear these values out of the way so we have some space. So we start with the first values here, which is 2 times 0 plus 5 times 3 plus 0 times 0. So 2 times 0 is 0, 0 times 0 is 0, so it leaves us with 3 times 5, which is 15, so our middle value is 15. And then we'll do one more, just so that way everything is super clear about what's going on here. So it's on the third column, on the second row, so we use the third column of matrix B and the second row of matrix A. So what have we got? Our first value is 2 times our first value is 6 plus our second value is 5 times our second value here, which is 4, plus our third value, which is 0, times our third value, which is 1. So 2 times 6, that's 12. 5 times 4, that's 20. 0 times 1 is 0. So what is that? That is 20 plus, good maths here, plus 12 is 32. So our values are 32. So if I actually put these values into my matrix calculator, so you can see here it's got 1, 2, 5, 1, just like the example we just used. And the second one's got 3, 0, 6, 0, 3, 4. It's exactly the same example, and then I calculate them. I get the results back. And as you can see, if I match the two, we had 3 in the top, we had 3 in the first column, 6 in this one, 15 in this one, 32 in the other one. So that's how you multiply two matrices together. And I think, other than getting into more complicated ideas, I think that's a good overview. It'll at least give you something to get started with, and we can start implementing these matrices in our actual engine. So let's go and do that right now. So let's start, and we'll use a new JavaScript file just to keep these separate, and so everything's nice and clean. We'll call this class m3 by 3. You don't have to call it that. It's just let us know that it's a matrix of 3 by 3. And we'll save this as a new document. We'll call it maths.js because I call it maths. I'm sorry, but I ain't changing for no one. So let's set up a constructor for this, and it doesn't take in any values, but let's create a new object to represent our matrix values. And it's of one, so we're just going to use an array for this, and we're going to make the first value the identity matrix. So first value is 1, 0, 0 like this, then it's 0, 1, 0. Like I said, best way to remember an identity matrix is that it goes on a diagonal. The ones go on a diagonal down, values like that. Okay, so we're going to create a few values to represent our different elements in the array. So we're going to call it m00. So our first 0 here, that's going to represent which column we're using, and the second 0 here is going to be which row we're using. So the first element is obviously going to be 0 column, 0 row. And then, let's see, we're going to go down the column. So our second index is actually going to be using our second row. So that should be a 1. And then that should be 2. And then we do it again. Only now it's 1, 0. So we're now using the second column. Like this. 3, 4, 5. Effectively, we're just identifying the different elements of our array as being from different row and column positions. So we don't always just have to intuitively know what element 5 is of our matrix, we can say, oh well, element 5 is the first column or the second column in the third row, sort of thing. Okay, and that's it. So since I just explained how to multiply two matrices together, let's just implement that. So we want to create, so whenever you multiply it, we want to create a new matrix that represents the result of the multiplication. So m free m, like this. So I create a new identity matrix, and then we set its values to output.matrix equals, and then a new array. And then we want to return that output. Oh, and this m is the matrix we're multiplying by. So let's do that. So whenever we're multiplying a matrix together, the what way we will do that? So we have matrix m multiply by matrix n, like this. M, if we go back to our diagram here, m is going to represent matrix A, and n is going to represent matrix B. So we go this dot matrix, referring to our array of values, and then we're going to get m free. We're going to take the, so this effectively is our top left value. Dot, so it's dot m000. We multiply that by the same position in our second matrix, like this. M free by free dot m00, this. But then we also want to add it. We need to step down into the next row. So, sorry, we want to go in matrix A, we want to go across the column, but in matrix B, we want to go across the row, like that. And then we do that again. So 2 and 2. Okay. So then the second element of our array is going to be this one here, which was 6 here. So it's going to be the second row multiplied by the first column. So let's just implement that now. We're going to speed through these just because there's 9 of them, and I'm not going to make you watch in real time as I put in all these values. I'll show you the end result at the end. Okay, so that's it there. It's completed. You can have a wee quick look through that just to see what's actually what I've done here. But so I effectively recreated what you saw me do with this diagram here, with the different values multiplying across the column in matrix B and in the row of matrix A. So that's 9 calculations overall, and this is the order that you do them in. If you want to take a moment just to look through that and make sure that you've got it right. So now we have that written up, we can import it into our document like this, and hopefully we'll just quickly check to make sure there are no awful typos. Oh, unfortunately there is. I forgot to put in commas at the end of those lines there. Just make sure you have those in. Oh, and make sure you haven't left this line in like I have. That was just to illustrate how it would work. Okay, so no major errors. And just to give this a test, let's just actually do some matrix algebra just to make sure that we get the right result back. We'll do that example that I used in the graph. So we'll create 2 matrices. So let m equal, let's see, new m by like this. So new matrix. We'll create 2 of them, n and m. And then we want to set m's values to, so the same values as matrix A. And matrix A looks like this. So 1, 0, 0, 2, 5. Okay, right. So I'll quickly input those values, and you can see how I change the values. Normally you won't want to change the values so directly like I'm about to do, but it's just for the sake of doing a test. Alright, I've set up my test here, so let's just make sure that doesn't have an error. Oh, it does have an error. Looks like I forgot a capital M on line 12. I've just forgot to capitalize those, so I'm going to find and place. So we're just going to test this, and if I refresh the page, we can see that I do get this console alert here. So let's see what actual values are in that. So if I open that up, we can see the first. So what we're expecting to see is the same values as we had here. So 3, 0, 6, 6, 15, 32, 0, 0, 1. And our order of numbers goes down like this. So the order should be 3, 6, 0, 0, 15, 0, 6, 32, 1. So let's just have a look and make sure that worked. So 3, 6, 0, that's what it said, isn't it? 3, 6, 0, 0, 15, 0, 0, 15, 0, 6, 32, 1, 6, 32, 1. So there we go. We can see now that our multiplication function is working as we expect it to. So that's good. Now that we know that our multiplication is working, we can then start building on that. Let's just get rid of our test here. So remember before when we were looking at this diagram and we were changing these last values here to transition our points across. So you can see here the values here in the last column, which I'm going to call from now on column 2. So that's column 0, column 1, column 2. By changing the values in column 2, we can change the position of our vectors. So let's just do that now with our matrix. So we want to output a new matrix like I've got here, and we want to take in the values that we currently have in the matrix. So we go matrix M3 by M like this, and then our first value, row 0, column 0, and we don't do anything with that. We just simply take the value right back out again, and then in the next column do the same thing, and then the next column we do the same thing. So the first column doesn't change, and then the second column also doesn't change, so we just do same values again. So this doesn't change at all. But in the third column, that's when we start wanting to make a change, and this gets a little bit messier this time. The value for the first column is going to be x times whatever is in this dot matrix. Effectively what we're doing here is a kind of matrix multiplication, but since we just want to make this simple, I'm just going to get through it. And so x multiply 0 row 0 column plus y times this dot matrix. This time it's column 1 row 0, and then we want to add that to this dot matrix m for m dot m2. So column 2 row 0. Okay, and then we do something similar for the others, except for this is 1, this is 2, so we just move down the rows, 1, 2, and 1, 2. And there you go, that's effectively our transition function. But we also want to have a scale function as well, so scale by x and y. And remember, again, back to this diagram where I showed that you can change the scale by adjusting these values here. So effectively we want to multiply across these rows and columns so we can scale our vector positions up like that. But we start off with the same sort of thing. Var output equals new m free m, so we create a new matrix to output. We set that output dot matrix equals a new array, and then we want to return output at the end. So it's just the calculations that change this time. So we want to multiply x down the first column, y down the second column, and then there's nothing to multiply down the third column. So let's just get that done. So let's just do a little bit of copy and pasting. This dot, so our 0 column, 0 row multiplied by x, and then we go down this column, so in the second row it's multiplied by x, and in the third row it's multiplied by x. Then we move on, shift over to the next column, and this time we multiply by y, like that. And then for the final column we don't do anything with it, we just simply put the same numbers back in again, like this. I still can't believe I made a trigger joke at the start of this video. I think our matrix is not too bad. Let's see, make sure, I'll just do a refresh. Doesn't seem to be any errors, seems to be working okay. The last thing I'm going to do is going to write a quick class, just for convenience, above this one. And all this is going to be is class, point, and a point is just going to be an x and y position. X equals some default values, x equals 0, and y equals 0. What am I doing? I'm not even using the right syntax. Constructor, like this, and then it's going to have the values this x equals x, this y equals y, and so that way we have a nice class that wraps up our x and y into one package, and we can expand this later with some more interesting functions that'll make our lives a little easier later on. But now we have a point, and now we have a matrix, free by free. Right, okay, that was a lot of maths, and maybe let's just take a little bit of a break here. One thing I want to do is I want this, I want our actual WebGL context to fill the window. So a little bit of a break, something nice for a while. And we can do that by adding in a window dot add event listener, resize, and then the callback function. I'm just going to put a wee alert here just to make sure it's working. Resize. So whenever we change the size of the window, we should see this. There it is, resize. Okay, so that's working. And then whenever we do that, we want to go window.game.resize. And we want to pass it the new window size. So, and to get the new window size, we type in window.inner width, like this. You can see it's 944 in this example. So we just pass in window.width, our inner width, my bad, and window.inner height. And then we just need to write our actual resize function in our game to catch that. So resize x, y, like this. And then we want to change the actual size of our canvas. So this dot, what do we got? This dot canvas element dot width equals x. This dot canvas height equals y. And so hopefully when we resize it, yep, the canvas stretches to fill the available window. Although one thing it should do, it should automatically run that resize right at the beginning. Let's just copy and paste this here. And there we go. Whenever the app launches, it fits the available window size, and as I change the size of the screen, you can see the actual window does adjust, squashing our sprites and everything else. So what about the way our sprites squash like that? Well, I explained in the last video the reason why it's doing this, because it's drawing a sprite between 0 and 1, and the WebGL plane is always divided up into from 0 to +1, and from 0 to -1, and from 0 to -1, from 0 to +1. So we probably want to do something to scale that, and we can use our brand new matrices That's right. It wasn't for nothing. We're going to actually put them to work and get them to do something useful for us. Oh, about time. Right. So how do we do that? Well, first of all, I want to create a new matrix here, and I'm going to call it world space matrix. It's going to equal a new matrix free by free. So it's just going to be an identity matrix for now. And whenever we change the size of the canvas, we want to change the free by free matrix. So what we're going to do is then change the value on resize to reflect these values. So equals new matrix free by free. Then we want to transition it. Nope. Transition. And say, remember whenever I said before, this goes from -1 to +1. So we want the top, this corner here to be, we want this to be 0, 0. So we want this to be the origin point. So what way we do that by first subtracting 1. It's a range from -1 to +1. So if we -1 from that, then it'll be a range from -1 minus -1. So that effectively is 0. So effectively we'll be shifting this canvas over to the left by half the screen. So transition by -1, and we want to do the same thing, -1 from the vertical axis, and by making it 1, so -1. Sorry, I'm saying -1 a lot, and it's just going to make it confusing. So all I really have to know what I'm doing is I'm transitioning this origin point here over to the top left corner, and we do that by creating a matrix with transition -1 and 1. And then what we want to do is we want to also scale it, and we want to scale it by the amount of let's say we want to scale it to fit like a sort of an understandable screen space. So how do we do that? Well, the X value we'll get back to. Since the total range of the screen is 2 wide, we do 2 divided by how many ever pixels we want the screen space to represent. And since we're doing kind of a pixel based thing, I'm going to make it 240, because the old NES games and like 16-bit games use 240 vertical lines. So yeah, we got 240 here. And so effectively what this means is that our range will be from 0 here, and the bottom of our window will be 240. So effectively we're going to shrink everything down so that way our range is bigger. And for our X, it's going to be a little bit more complicated because we're going to have to work out a couple of little things here about the screen width. So let's see, we'll call it W ratio. And what we're going to do is we're going to take the X, which is the width of our window, and then we're going to divide it by the height of our window, Y, divided by 240. So that'll give us our ratio of our space across the x-axis. And then what we want to do is we want to take, again, same thing here, 2 divided by W ratio, like this. Oh, and one last thing, this 2 here, divided by 240. Well, let's make that -2. And the reason why I do that is effectively by using a negative number, it flips the entire image upside down. So instead of going between 1 and -1, it'll go from -1 to +1. So it'll basically flip everything around. And then because it's by 240, instead of going from, it'll be from 0 to 240. Oh, this stuff. I know. You know what the worst part is? It's actually kind of simple. I imagine you probably have a grasp on it, but explaining it, that's the real nightmare of it. And all you're doing is saying numbers over and over again, but the concepts behind them are pretty straightforward. It's just that explaining them with words can be pretty difficult. But I hope this makes some sense to you at all. And if it doesn't make any sense, just copy this, and then you'll see later on what this does. But I'm sorry I can't make this any clearer at the moment, but I am struggling. And just to make sure, oh no, what have we got? We got an error. At line 31, what's the problem? Transition is not a function. Did I spell it wrong? Transition. I spelled it wrong here. Okay. Whew. So let's just take a 5-second break just to catch our breath and think about what we're going to do next. So we have our new world space matrix. So we're going to have to bring that into our vertex shader. And this is our vertex shader. You might remember it from part 1. So we're just going to have to create a new uniform, and we're going to call it uniform. It's going to be a type mat free, which is a 3x3 matrix. So you can see already, that these things are interrelated. Like these concepts of matrices and stuff are very much hard coded into OpenGL. They're pretty much the standard. So we have and we want to call this one U underscore world. Let's spell it right. And then we want to take that matrix and we want to multiply it by our vector like this. So we have a vector 4 and it's going to be multiplied by world, which doesn't work because remember I said before that a matrix. Remember I said before about how a matrix can only be multiplied by something with the same number of rows. Well, this here has 4 rows effectively, and our matrix only has 3. So let's just change that around a little bit and take away one of these values. However, this GL position does require 4 values, so what I'm going to do is then just do vec4 and wrap the entire thing up like this and create a vec4 out of the resultant of this matrix multiplication. And that seems to be working. We can't see anything because effectively we're multiplying it by an empty matrix, a matrix values all zeros. Anyway, so let's actually set this value. And we do that by going back into our material and back in the sprite here we pull out some values out of our shader. So let's pull out some more values. So our world value is get uniform location. We call it U world lock like this. Alright, and then we need to set that value at the end of our render function before we do the draw arrays. So we go GL uniform, my typing, matrix, because it's a matrix type free, and it's a float, and I don't know what the V stands for, but there it is. And then we take our position that we get here, which is U world location, and then we need it to set to, if we get our window dot game and use the world space matrix that we set up here, and then the last thing we need to do is we need to turn it into a float array. So I'm going to do get float array like this. And we need to add get float array to our matrix class. So get float array like this. Doesn't take any parameters, and all it's simply going to do is go return new float 32 array. And then we put in this dot matrix. And that should get a float array out of our array values. Okay, so I expect errors, but hopefully, fingers crossed. Well, no errors, but we didn't exactly get anything useful back. So why not? If I comment this out, it means that we'll just be using the identity matrix that we first initialized. And then we refresh it. So we get the same result back because we have an identity matrix, which doesn't make a change. So we at least know we're able to set that value, but I don't quite know what's gone wrong here. So let's look at it in a bit more detail, and we'll slowly build this up and see what results we get. So we're going to just do dot matrix equals new matrix free by free, which shouldn't have any effect. Then we're going to transition it. Transition, and let's say -1 by 1. What's our result back? We get nothing back. Okay. What if the values of the transition were 0 by 0? Okay, it seems to be fine. And if we set it -1. So yeah, by setting it to -1, it's now set the origins over here in the top left corner. That's good. That's what we want. However, we do also want to set the origins here. So I think I know what's gone wrong here. I think whenever we set this value 1, we're pushing our entire image out. So if I set it to 0.5, I bet it comes back. Yeah, there it is. Just slightly out of the screen. So we're just going to leave this as 0 for the moment. We're going to work on the scaling part of it. So we want to scale it. We want to scale it, let's say 1 by 1. This shouldn't have an effect. Yep, let's get the same result back. So let's try scaling the y. So y divided by 240. And that seems to have worked, although it's absolutely compressed our image into like a pixel wide. But what if we make it, right, we'll just make it divided by 2, so it should do nothing. But we'll make this -2 to see if it does indeed flip our image upside down. Well, that's good. It has flipped our image up the right way. So we make this 0.5. That should start pushing it up to the top of the screen. And if I make it 1, okay, there we go. We've now pushed our image origin to the top left corner of our window. And if we make this 240, I think the problem is, yep, there is our image. You can just about see it at the very top of the window, but it's so compressed that it's barely visible. So I think that was the problem all along. It wasn't that it wasn't displaying anything, it was just that it was displaying something so small we couldn't see it. I can't quite zoom in to show you, but I'm pretty sure there is a tiny image right in that corner. So I think we can move on from now. Let's get rid of this. We just need to make our sprite bigger. Before, it was set to create a sprite that is 1 by 1 pixel. So effectively that's what we've done. We've reduced our sprite into a 1 pixel tall thing. So we need to make it bigger than that. And to do that, I'm going to start taking in additional parameters into our sprite constructor. So let's just set something, we'll call it options. Well, an abbreviation of options. And we want our sprite to have a width and a height. So this dot, we'll call it UV equals new point, and its default values are going to be 64 by 64. But we go if width is in our options. Oh, as well, our options should also have a default value in case they're not specified. So if width is present, then we go this dot UV. Oh, actually, let's instead of calling this UV, we'll call it size. This dot size x equals options dot width times 1, which will ensure that the value ends up being a number. And we go height with the same thing. So if height is in options, we then set size y to be height. Okay. That seems sensible. Now, whenever we create our sprite's geometry, instead of letting it default as size 1 by 1, we'll make it these values, this dot size dot x, and this dot size dot y. And that should, yep, there they are. There's now 64 by 64. So we can now see them again, which is good. Right, and I'm going to use a different sprite from here on in. Just something, like these two sprites are very similar with the same sort of specifications. So I'm going to make them use different sprites with different specifications. And just to show you what we're working with here, I've got some new sprites here. So we've got this little fireman, and he's got quite a unusual size. You know, he's 48 by I think it's 48 by 48, and we want to use this walker here, and that's going to be 64 by 64. So they're going to use different parameters, so we're going to show that working in action. So let's call this first sprite is called Man on Fire, and this second sprite is called Walker. So we're going to bring those in instead of the ones we had previously and refresh. There they are in place. And then we want to specify their width and height. So man and fire, like I said, is a width of 48 and a height of 48. And then for our walker, it's going to be a width of 64 by a height of 64. So when I refresh that, it's a bit of a muddle, but yes, indeed, we do have two very different sprite sizes, and that's what we want. Now, the thing is with sprites, at the moment we're drawing the entire sprite, well, the entire image, so you can see all the different frames of animation here already being displayed. But really with a sprite, you only want one of these animations to display at a time. And to do that, we need to control the UVs of our objects. So let's just get started on that. First of all, we want to change the material. So our texture coordinates here, we want to adjust them and add a new property, and we'll just call it uniform vec2, like this, and we'll call it uframe. Uframe Roger Rabbit, uframe Roger Rabbit, and we just want to add it to our texture coordinates like this. So this is a variable that we can change. So we go back to our material, and then in addition to our uworld location, we want to get our uframe location, like this, and we'll set the value here, and it's no longer uniform matrix, it's going to be just a uniform, it's going to be uniform 2, as in it's a vector 2, and it's a float. And instead of all this, we want it to put in some value, frame X and frame Y. Okay, but we also need to change the actual mesh itself. And so let's just create, let's see, let UVX equal, so we get the size, the size of it, dot X, divided by the image's original size. The way texture coordinates work on an image is that an image, no matter what size it is, goes from the range of 0 to 1 in both axes. So even though our image is going to be like 256 pixels, we don't necessarily want to put in 256 or 64. So what we do is take 64 and we divide it by the original image size, which will give us a value between 0 and 1, and that way that'll give us something that we can scale up. So we do the same thing with the Y as we do with the X value, so put that in like this, and then we create our new UV coordinates based on UV X and UV Y, and with any luck we should hopefully get an error. Okay. Alright, because we defined these frame 1s and frame 2 which don't do anything yet, so we'll just comment that out for the moment. And no, that still hasn't worked. No, why hasn't that worked? Oh, right, this is a typo. That should be a comma, not a full stop. Ah, there we go. That's brilliant. So there you go. You can see now it's only displaying one sprite at a time. That's really, really good. That's huge progress. So great. We're nearly there already. So now we just need to we want to animate these things, and we want to have them move across the screen and just generally move a little bit. So how are we going to do that? So we have this render function here, and it does at the moment doesn't take any properties, but let's start putting some properties in. So the first one I'm going to take in is position, and then I'm going to take in something called frames, and these are going to be of both type point. So down here we had frame X and frame Y, so let's just get those values. So let frame underscore X equal, and then we go math.floor, and we get the X value of our frames. We floor it because we don't want any kind of values in between frames, otherwise it'll look very strange. And then we multiplied that by our UVs. So up here we just made those are variables, just you know, relative to this block. So instead of doing that, we'll just make them variables as member of the class entirely. So this.uvx, this.uvy. So instead of being local variables, they're now object variables, and then we just change uvx to uvy like that, and that's pretty much it. So yep, so now we take the frame's x position and we multiply it by whatever uvx is, effectively shifting along our uv position, you know, by so many units into our image, so that way we're effectively getting the next sprite across. And then the same thing is true of the UVY, except it's the next sprite down. So frame X and frame Y. So we now have those are now being set. We have no way of changing them, and we still haven't provided them, so at the moment it's like, what are you telling me? I don't understand what these values are. So I'll put them in quickly here, just for the purposes of testing. Now you obviously don't want this in your final engine, but I just want to put it in here just so you can see it working. So we'll go sprite 1 position is equals new point, and sprite 2 position equals a new point, and then we want to do sprite 1 frame is going to equal a new point as well, and sprite 2 frame looks like this. And we just put those values in like this. For both our sprites. Like that. And then hopefully, yep, that's great. So that seems to be working. So let's test this in the console. If we change the value of the frame sprite directly in the console, we should see some changes live on the screen. Frame 2 like this, and X, you see it's set to 0, and if I set it to 1, it'll be the next frame over. If I set it to 2, it'll be the next frame over. But if I set it to 3, that should go outside the range, so it should disappear. And then back again. And then if I set the frames Y to 1, it'll be a different frame. So there you go. That's sort of the idea. By changing the X and Y of whatever frame we're using, changes the UV position, which has the effect of effectively changing what frame is being displayed. But let's get a little bit of animation going. And we can do that by, let's see, sprite 1 frame. So we're going to take the frames X and we want to make it increment along. Let's see, how are we going to do that? We're going to make it go equal. We'll do this in a really nasty way. You obviously don't want to do this generally, but if we go date times not 1 like this, and we want to go across, let's see, if I show you my sprite again. Which one's this? Sprite 1, that's Man on Fire. You've got 6 walking frames, so the first 3 are on the top, and then the next follow-up 3 are below it. So we need to go 1 or 0 0 0 or 0 0 1 0 2 0 0 1 1 1 2 1. Okay, so we need to go across those like that. So the way we're going to do this, we're going to use a bit of modal mathematics. And if I just set it up like this, you should take the date, multiply it by 0.001. So date will return like the time in milliseconds. Then multiplying it like this here with a number that small means that we'll effectively get it 1 second. So every second should hopefully update the frame. And there we go. We can see him moving. Oh, it's maybe a little slow, so we'll maybe make it 5 times faster. So every 1/5 of a second, the frame updates. Here we go. We can see it going. And then we'll do a little bit of funky modal mathematics to make it go through the entire walk cycle. There we go. Now he's going through all of his animations, and I'll do the same thing with sprite number 2 as well. So sprite 2, and I think sprite 2 is laid out in the same way. Yes, it is. You can see here that the first 3 frames of the walk cycle are on the top, and then the next 3 frames of the walk cycle are underneath. So basically the same thing. And there we go. Brilliant. Right, so then what else do we want to do? We want to make one of these sprites start moving. So we go this dot sprite to position dot x equals, and then I don't know, itself plus 0.1 or something like that. And if it reaches 256, we use a bit of modal mathematics to make it go back to 0. And this shouldn't do anything because we haven't hooked it up yet, but no errors. Okay, so sprite 2's position gets passed over to our material's render function. So here it is here. So how do we actually change this position? What's that? Another matrix? You're damn right. So let's get our second matrix set up. If we go back to our vertex shader, we set up we have view world, which is affects its position on screen. So now we want to say U object, something like that. And by the way, something to bear in mind is that the order you multiply matrices is important. So we want to multiply it by the screen space and then by its own local space. So just bear in mind, yeah, U world multiplied by U object multiplied by the actual vector position. That's the order this thing should go in. Alright, so we have our U object matrix. So let's set that up so we can read it from our material. And we just go U object like that underneath this one. And we get its location like that. And to speed things up, we'll just simply copy and paste the one above, put it in our position, and then we need to create a new matrix. So let ob mat equal new matrix, new mat free by free, like that. Okay. And then all we need to do is transition it, transition that matrix by whatever position. Oops, sugar me baby. Position X and position Y, like that. Okay, so we take an identity matrix and effectively transition it by whatever position we push in. So as the position goes up, we should hopefully see the object move across the screen. And then last thing we do is, we do get the matrix, get float array, and then we assign it to the U object location. And with any luck at all, there we go. He's going very slowly, but he is going. We can speed him up a little bit. Let's make this 1.1. And there he goes. Excellent. And then he should return back to the start. Brilliant. So, you might have been thinking earlier, what was the point of all that screen space stuff? You can see here that whenever I scale the window up, that 240 pixels going down the screen stays the same. So what it does is scales the sprites down to actually fit that window. So we still have the top left corner origin being 0, 0, but 240 pixels down will actually get smaller to accommodate the smaller window. But the way we have also set it up is that way the width is based on the height. So as we reduce the width of the window, it doesn't actually affect the scaling of any of the sprites. We still have 240 lines going down the page, but the amount of lines going across the page is based on how much available space there is. We don't have any ugly stretching of any of our sprites, and everything there looks very nice and consistent, and now I can scale the window up as big as I want, and things still look really nice. Check that out. There you go. Not too bad, is it? We haven't really started into the logic of the game yet, but getting the basics of the rendering down, that means we're getting very close to the point where we can start thinking about game logic. But there are still a few more things I want to introduce you to about how rendering works and stuff like that, but I'm going to save that for the next tutorial. If you want to get the final code here, I have put the entire thing up in GitHub. The URL will be in the description, and what you can do is download the different branches as they come out. So we have the last episode, and then I'm going to create a branch for this episode. So if you want to jump ahead, you'll be able to download last week's code and then build from that, and that'll be true of the coming weeks as well. Anyway, I hope this has been useful for you, and thanks for watching as well. So I'll catch you next time, and have a good day. Bye!